The USS Gerald R. Ford weighs 100,000 tons when fully loaded. That's roughly 71,000 family cars, all moving together as a single object through hostile water, and on top of that, 5,000 people are eating, sleeping, working, and occasionally launching 30-ton aircraft into the sky. Your brain tells you this is impossible, that something this heavy cannot float, let alone sustain a city of people for months without resupply, that systems fail, that people need too much. So we are breaking down exactly how it does work, the engineering, the logistics, and the daily reality of living inside the most complex machine humanity has ever put to sea. The population of Gerald R. Ford is larger than the entire population of Monaco, a nation-state floating with jets on the roof. The ship's galleys serve approximately 18,000 meals per day, 18,000 individual meals, breakfast, lunch, dinner, and midnight rations, prepared around the clock, 7 days a week, for up to 90 straight days at sea. The ship itself runs on 2 nuclear reactors, which means it never needs to refuel for the life of the hull, approximately 50 years. The flight deck alone covers 4.5 acres of steel at sea, with FA-18 Super Hornets landing on it at 150 miles per hour. Most people assume the hardest part of life on an aircraft carrier is the danger. Explosions, combat operations, storms. And yes, those are real threats. But here's what nobody talks about. The hardest engineering challenge on this ship is making 5,000 people simply function, day after day, month after month, with no connection to shore. An aircraft carrier has a water utility, a sewage system, a power grid, hospitals, supply chains, all of it in one hull that moves. And if something breaks, the nearest city is thousands of miles away. This is not a ship with a city on board. It is a city that happens to float. Now we are going to break down exactly how it works, system by system. Level 1, the wire. Most people know about the arresting wire. A plane catches a hook on a cable, and the cable slows it down. Simple, mechanical, obvious. This is correct, and nearly useless as an explanation, because it skips the real question. How does that wire absorb the kinetic energy of a 30-ton aircraft moving at 150 miles per hour without ripping the plane in half? The arresting system uses hydraulic cylinders buried beneath the flight deck called arresting engines. When the tail hook catches the wire pulls those cylinders, forcing hydraulic fluid through a precisely calibrated valve. The valve creates resistance. Resistance creates deceleration. The tolerances here are extraordinary. Too much resistance, the hook tears out of the airframe. Too little, the plane goes into the ocean. The system has to self-adjust in real time, based on the weight and speed of each individual aircraft, every single time. On a Nimitz-class carrier, 4 wires are stretched across the deck. Pilots aim for the 3rd wire, not the first, not the last. The 3rd wire is the sweet spot. Missing all 4 means a bolter, full power, climb, come around and try again. And the pilot keeps full engine thrust during the entire approach, because if the hook misses, idle throttle means a 30-ton aircraft going straight into the ocean, but the arresting system is just one problem. The carrier is solving 5 other engineering challenges simultaneously, and they all run through the same hull. The flight deck is the part you see. What you don't see is what's underneath it, a vertical city 9 stories deep, running the entire length of the ship. The Gerald R. Ford has over 2,500 compartments. Not rooms, they are individually pressurized sections that can be isolated instantly in the event of flooding or fire. The ship is designed so that any 2 adjacent compartments can flood simultaneously, and the ship will not sink. But this is not just a mechanical response to water, it is an immune system. In 1967, the USS Forrestal caught fire after an accidental rocket discharge on the flight deck. The flames reached aviation fuel in minutes. 134 sailors died. The Navy spent the next decade redesigning how fuel, ordnance, and aircraft are positioned relative to each other on deck. Every design choice on a modern carrier exists because something went wrong on an older one. Now, ventilation. Almost nobody thinks about it, but it is one of the most complex engineering challenges on the ship. The reactors generate heat continuously. 5,000 people breathe and produce moisture around the clock. Aviation fuel evaporates. Jet exhaust from FA-18 engines accumulates on deck. All of this is inside a sealed steel box with no windows. The ventilation system moves millions of cubic feet of air per hour, continuously filtered and routed through fire suppression zones. If it stops, the city does not suffocate immediately, but degradation starts within hours. The ship produces its own fresh water from seawater, over 400,000 gallons daily, cleaner than what most Americans drink at home. 3 separate electrical grids run in parallel. If one fails, the others compensate automatically. Medical care. The ship has a full hospital with operating rooms, X-ray, and an intensive care unit. Surgeons perform appendectomies and open-heart surgery while the ship rolls in the Pacific, thousands of miles from the nearest coast. This is not a medical bay, it is a hospital that decided to go to sea. Sailors sleep in racks, beds stacked 3 high, each roughly the size of a coffin. For months it is home, but here is the part nobody mentions. The crew sleeps in 3 rotating shifts. While one shift sleeps, 40 feet above their heads, 30-ton aircraft are launching. The punch of the catapult, the roar of turbines, the crack of the arresting wire, and the sailor below just sleeps, because in 6 hours, it is their turn on deck. Every one of these systems runs in redundant parallel loops. No single point of failure can take down the city. Most engineers would stop here and call it a logistical triumph. But there is a third level, and it is the one that explains why the Gerald R. Ford represents a genuine break from everything built before it. Level 3. The engineering shift. First, the reactors. The 2 nuclear reactors are watched around the clock by personnel who went through nearly 2 years of intensive training just to be allowed near the reactor compartment. The standards are the highest in the fleet. The margin for error is 0, not because it is written in a manual, but because the alternative is 5,000 people adrift in the middle of the ocean with no power, no water, no food. That's why the ship has 3 independent electrical grids. If one fails, the other 2 compensate automatically. Now, the catapult. The Gerald R. Ford class replaced steam-powered catapults with the Electromagnetic Aircraft Launch System, EALS. This was not an upgrade, it was a philosophical shift in how the ship manages energy. Steam catapults require massive pressure buildup before each launch. The force profile is uneven, maximum at the start of the stroke, tapering at the end. That is hard on the airframe, limiting what aircraft the system can safely launch. EALS uses a linear induction motor, the same physics as a maglev train, but horizontal and violent. The motor precisely controls its force profile along the entire launch stroke, applying exactly the right energy at every point in the acceleration. Less airframe stress, faster recharge between launches. A system calibrated for anything from a 65-ton FA-18 to a lightweight surveillance drone. The result, the Gerald R. Ford can theoretically generate over 33% more aircraft sorties per day than a Nimitz-class carrier, not because it carries more planes, but because the launch and recovery cycle is faster and more controllable. Here's the principle most people miss. Every engineering decision on a carrier is simultaneously a logistics decision, a maintenance decision, and a military strategy decision. Switch to electromagnetic launch, and you do not just upgrade a catapult, you change how an entire carrier strike group fights. Think of the carrier like a human body. The flight deck is the skin. The arresting wires and catapults are the muscles. The nuclear reactors are the heart, but the real work happens in the systems you never see. The circulatory loops of pipes and fuel lines. The nervous system of redundant electrical grids. The immune system of damage control teams and fire suppression. Remove any one of those systems, and the whole organism degrades. If the arresting system fails, aircraft and pilots go into the ocean. If fire suppression fails, fire spreads through enclosed steel corridors in minutes. If the electrical grid fails, the ship goes dark. 5,000 people, one hull, no margin for cascading failure. Here is what you now understand that most people do not. An aircraft carrier is not a ship with aircraft on it. It is a floating city that happens to have a runway on the roof, and the city is more complex than the runway. The hardest engineering problem is not launch or landing. It is keeping 5,000 people alive and functional for 90 days, with no shore, no resupply, and no margin for failure. And the switch from steam to electromagnetic launch on the Gerald R. Ford class did not just upgrade a catapult, it changed the ship's sortie rate by over 33%, which changed how an entire carrier strike group fights. The next time you see footage of a jet catching an arresting wire, that half second of screaming deceleration, you are watching the output of 9 stories of engineering, 2 nuclear reactors, 2,500 sealed compartments, a full hospital, and decades of hard lessons paid for in lives. That wire is not catching a plane. It is the last line of an engineering argument that took 100 years to write.